gets smaller than a pea.
Yes.
This is like
BB, actually. Yeah.
okay. Well, it depends. Not all peas are made the same, but this is like throwing a perfect strike in baseball from a pitch. This is like a journalist wrote this, I think. This is like, oh no, it's not a journalist. It's DOE wrote.
Yeah, it could
Department
be,
of Energy.
We try to use all these analogies.
This is like throwing a perfect strike in baseball from a pitcher's mound 350 miles away from the plate. There you go. Department of Energy. The United States Department of Energy wrote this. Okay. Can you explain what the lasers
what actually happens? Yeah. Actually, there's usually mass confusion about this. So what's going on in this form of energy? So the fuel is delivered in a discrete, the fusion fuel, the deuterium and tritium, is in a discrete spherical. It's more like a BB. Let's call it a BB. So it's a small one, and all the fuel that you're going to try to burn is basically there. Okay, and it's about that size. So so how are you going to get? And it's at literally it's like at 20 degrees above absolute zero, because the deuterium and tritium are kept in a liquid and solid state.
Oh, so wow! So the fuel is injected not as a gas, but as a solid.
It's actually, and it's very, and in these particular experiments, they can introduce one of these, these targets once per day, approximately, something like that, because it's a kind of amazing technology, actually, that I know some of the people that worked on this back in the day they actually make these things at a BB size of this frozen fuel. It's actually at cryogenic temperatures, and they're almost like smooth to the atom level. I mean, they're amazing pieces of technology. So what you do in the end is what you have is a spherical assembly of this fuel, like a ball. And what is the purpose of the lasers? The purpose of the lasers is to provide optical energy to the very outside of this. And what happens is that energy is absorbed, because it's in the solid phase of matter, so it's absorbed really in the surface. And then what happens is that when it's absorbed in something called the ablator, what does that mean? It means it goes instantly from the solid phase to the gas phase. So it becomes like a rocket engine. But you hit it like very uniformly. So there's like rocket engines coming off the surface. Think of like an asteroid almost, where there's like rockets coming off all this thing. So what does that do? Well, what does a rocket do? It actually pushes, by Newton's laws, right? It pushes the other thing on the other side of it, equal and opposite reaction. It pushes it in. So what it does is that the lasers actually don't heat. This is what was confusing. People think the lasers, we're going to get it to 100 million degrees. In fact, you want the exact opposite of this. What you want to do is get essentially a rocket going out like this. And then what happens is that the sphere, and this is happening in a billionth of a second or less, actually, this rapidly, that force, so rapidly compresses the fuel that what happens is that you're squeezing down on it and it's like, what was the... See, BB, that's bad, actually. BB, I should have started with a basketball. Goes from like a basketball down to something like this, in a billionth of a second. And when that happens, I mean, you scale that in your mind. So when that happens, and in this comes from almost from classical physics, so there's some quantum in it as well too. But basically, if you can do this like very uniformly and so-called adiabatically, like you're not actually heating the fuel, what happens is that you get adiabatic compression, such that the very center of this thing all of a sudden just spikes up in temperature, because it's actually done so fast. So why is it called inertial fusion? It's because you're doing this on such fast timescales that the inertia of the hot fuel basically is still finite, so it can't like push itself apart before the fusion happens.
Oh wow!
Yeah.
So how do you make it so? How do you make it so fast?
This is why you use lasers, because you're applying this energy in very, very short periods of time, like under a fraction of a billionth of a second. And so basically and then the force which is coming from this comes from the energy of the lasers, which is basically the rocket action, which does the compression.
So is the inward facing force? Is that increasing the temperature exponentially?
You want to keep the fuel cold, and just literally just ideally compress it. And then in something which is at the very center of that compressed sphere, because you've compressed it so rapidly, the laws of physics basically require for it to increase in temperature.
So
The
change
effect
in
is like,
pressure.
if you know the thing, so adiabatic cooling we're actually fairly familiar with. If you take a spray can, right, and you push the button, when it rapidly expands, it cools. This is the nature of a lot of cooling technology we use, actually. Well, the opposite is true, that if you would take all of those particles and jam them together very fast back in, they want to heat up. And that's what happens. And then what happens is you basically have this very cold, compressed set of fusion fuel. And at the center of this, it goes to this 100 million degrees Celsius. And so if it gets to that 100 million degrees Celsius, the fusion fuel starts to burn. And when that fusion fuel starts to burn, it wants to heat up the other cold fuel around it. And it just basically propagates out so fast that what you would do, ideally, you would actually burn, in a fusion sense, most of the fuel that's in the pellet. So this was very exciting, because what they had done was, it's clear that they propagated this, they got this, what they call a hot spot, and in fact that this heating had propagated out into the fuel, and that's the science behind inertial fusion.
So the idea behind a reactor that's based on this kind of inertial confinement is that you would have a new BB every
10 times a second or something like
and
this.
that there's some kind of so there's a incredible device that you kind of implied that kind of has to create one of those BBs.
So you have to make the BBs very fast. There's reports on this, but about what does it mean? The starting point is, can you make this gain? So this was a scientific achievement primarily,
right.
because
and the rest is just engineering.
No. The rest is incredibly complicated engineering. Well, in fact, there's still physics hurdles to overcome. So where does this come from? And it's actually because if you want to make an energy source out of this, this had a gain of around 1.5. That, namely, the fusion energy was 1.5 times the laser input energy. Okay, this is a fairly significant threshold. However, from the science of what I just told you, is that there's two fundamental efficiencies which come into it, which really come from physics, really. One of them is hydrodynamic efficiency. What I mean by this is that it's a rocket. So this just has a fundamental efficiency built into it, which comes out to orders of 10%. So this means is that your ability to do work on the system is just limited by that, okay? And then the other one is the efficiency of laser systems themselves, which, if their wall plug efficiency is 10%, you've done spectacularly well. In fact, the wall plug efficiency of the ones using that experiment are more like 1%, right? So when you go through all of this, the approximate, place that you're ordering this is for a fusion power plant would be a gain of 100, not 1.5. So you still, and hopefully we see experiments that keep climbing up towards higher and higher gain. But then the whole fusion power plant is a totally different thing. So it's not one